Hey guys, welcome back again to the Maths Club. If you are just joining us, so welcome. If you have not subscribed to our channel, please subscribe and engage with our videos. I'll encourage everybody, if you know somebody that this can help, please introduce them to the channel. That is the essence of all we're doing, to reach as many people as possible. So continuing with our series on set theory, we're going to be talking about the 7 laws of sets. So if you have not seen any of all those previous videos, you want to check the playlist in the description below and start from the beginning so that you can get the full content of what we have delivered. So there are 7 laws of sets that bind all the operations that we do in sets, and we're going to discuss each of them and look at examples to bring them home. So the first law is Idempotent Law. What does idempotent mean? Let's see. It is denoting an element of a set which is unchanged in value when multiplied or otherwise operated on by itself. So an example is, if you have the number 1, if you do 1 times, if you multiply 1 by itself, will it change? No. So 1 times 1 still remains 1. So that is like a very close example, but let's see it's in set theory. So an example is, you have a set A and you're doing union of the set A. So you want to join A union A. You know, we said A union A is a combination of the elements in both of the sets without repetition. So I mean, it just makes sense that if I do A union A, I'm still going to get A back. Just like when you have 1 times 1, you're still going to get 1 back. And if I do A intersection A intersection is just things that are common in both sets. So if I do A intersection A, that's going to give me A. Let's see some examples that will just bring it home. So this one says, if set A is equal to 1, 2, 3, we should find A union A and A intersection A. I already know that from the idempotent law, A union A is going to give me A and A intersection A is going to give me A. You can try it out. So from here, I know that the answer here is going to be 1, 2, 3, and the answer here is going to be 1, 2, 3. Right, so I could say from the law of idempotency, A union A is equal to A and A intersection A is equal to A. The second law we're going to be looking at is the associative law. And what does that mean? In mathematics, whenever we have associative law, it's always about brackets and moving the brackets. So you're seeing this first guy, the bracket is saying A union, then, you know, of course, if you remember BODMAS, brackets comes first. So that means in this particular thing, I'm going to find B union C first. When I find B union C, the result, I will now do A union of that result, right? And they're telling me that as far as the union and union here, right, it does not really matter where the bracket comes from. So either the bracket is on the second and the third, or the first and the second, they're still going to have the same results. Same thing too for the intersection. As long as it's intersection and intersection that is here. So if it was union and intersection, that is a different thing. In this case, we have intersection and intersection. As far as it's the same operation, wherever the bracket lies, it does not really matter. Let's say an example to bring that home. So if you have set A as 1, 2, 3, 6, set B as 4, 5, 6, and set C as 6, 8, 9. We want to find A union B union C, A union B in brackets union C, A intersection in brackets B intersection C, in brackets A intersection B intersection C. So let's solve this. For this one, for this number I first, remember from BODMAS, I have to do B union C first. So if I do B union C, that is going to give me what? So I'll have 4, I'll have 5, I'll have 6, I'll have 8, I would have 9, right? Great. So if I now do A union this particular guy, what would that give me? So A union B union C, right? That will give me what? 1, 2, 3, 4, 5, 6, 8, 9. So if I close it here, this is 9. If I close this here, and this is my answer for this particular. I want to try the II and see if we're going to get the same thing. Welcome back. What did you discover? You had the same thing, Abi. Great. So let's do III, and that will be A intersection B intersection C. So I have to first find what's in the brackets first from BODMAS. So if I say B intersection C, what would that give me? So what is my B? What is common in B and C? What is common in B and C is just 6. So let's see. Let's just say 6. So A intersection B intersection C. This would be what? What is common in A and this B intersection C, which is 6. So the reason that's common both of them is 6. So I mean, at the end of the day, the answer for this is 6 when I do the intersection, right? If any of this is looking strange, you can watch the previous videos that we've done on set operations. We talked about intersection, union, and complement. Now I want you to try the number 4 by yourself. A intersection B intersection C. Welcome back. What did you discover? You add the same thing, Abi. So that is in line with the law of association, right? That as far as the same operator in between them, you are going to get the same value. Let's see. So we had 1, 2, 3, 4, 5, 6, 8. Yeah, so we had 1, 2, 3, 4. So that's correct. So the same thing to here. We had 6 and we had 6 here. Now the next law we're going to be looking at is the commutative law. So what's commutative law? So if you look at normal addition, if I say 1 plus 2, 1 plus 2 is equal to 3, right? Also, so if I say 2 plus 1, 2 plus 1 is also equal to 3. So it does not matter where each of the operands, when I say operands, the things I'm trying to add. So if I put 1 first or I put 2 first, it does not matter. Because the law of commutative says that in that kind of situation, regardless of how I position the 1 and 2, I'm still always going to have the same results, right? So just a multiplication, so 1 times 2, 2 times 1, same thing. So addition and multiplication are commutative. So for this law, same thing. So if I have A union B, same thing as saying B union A. If I have A intersection B, same thing as saying B intersection A. And let's look at an example to just try this one. So I have sets A, which is 1, 2, 3, 6, and B, which is 4, 5, 6. And I have to find A union B, B union A, A intersection B, B intersection A. So if I do this A union B, what am I going to have? Like I said, I always try to do everything in ascending order so I don't miss out on anything. So from set A, I have 1, 2, 3. Set B, I have 4, 5, and then the 6 that both of them share. Yeah. So I want you to try B union A and see if you got the same thing. Welcome back. You had the same result, Abi. Yeah, this just proves the commutative law. So if I have A intersection B, what would this be? We have 6 that is common, right? What else do you have common? I think there's nothing else common, so this should be 6. And you also want to try B intersection A yourself. Welcome back. What did you have? You add 6. Great. So this is our values, yeah, so that we have the same thing. We have 6 and we have 6 here. The next law we're going to be looking at is the distributive law. Now, what do you notice here? In this case here, you can see that it is not the same sign now, right? This is intersection, this is union. So how do we solve this? If I show you how we used to solve brackets in normal mathematics, if you had 2 times 3 plus 2, right? One way to solve this is like saying 2 times 3 plus 2, which is 5, right? And this will give you 10. And that way to solve this is by saying 2 times 3. So you can say 2 times 3 first, then this operator, which is plus 2 times 2. 2 times 2. Right? So what did I do? I said 2 times 3, then whatever I join them plus 2 times 2. So basically, I'm multiplying each of these values here. So I'm multiplying this 3 with this 2, and I'm multiplying this 2 with this 2. That's basically what I'm doing. So I'm just trying to increase whatever this value is by the multiplication of this, and I'm trying to increase this value here by the multiplication of this. So 3 will multiply the 2, and 2 multiply the 2. So at the end of the day, I'll have 6 plus 4, and that'll give me 10. If we bring the same thing to light here, we have A intersection B union C, right? All we're just doing here is A intersection B union A intersection C. You can see it. If we compare this to this, I said this is A intersection B union C, right? So just like I said, 2 times 3. So and add 2 times 3, I will say A intersection B, and then the operator here, which is the union what? 2 times 2, which is A intersection C. So that's basically it about this particular operation. So whenever you're solving a particular question and then you're seeing something like this, an easier way to do is that you can just find A intersection B, A intersection C, and find the union of both of them. All these laws are just ways to solve these questions simpler. Same thing too for this other guy. So we have A union B, right? Then whatever you join in both of them in the brackets, intersection A union C. Let's look at an example that will bring this home. So if you have sets A, B, and C, I'm told to find A intersection B union C. Intersection B in brackets union A intersection C. A union in brackets B intersection C. In brackets A union B intersection in brackets A union C. Let's solve this number 1. First, I have to find B union C. like I said, always in alphabetical order. I'll just do 1 4 5 6 9. So that would be 1 4 5 6 9, right? And A intersection this, so A intersection this guy, what do they have in common? They have 1 and they have 6. So A intersection B union C 1, 6, right? Great. Now alternatively, if I knew the associative law, I could just do this number 2 step instead, and we should have the same value. Let's see. If I do A intersection B, A and B, what's common in A and B? Only 6. And if I do A intersection C, A intersection C only has 1 in common, right? So I could just come and say 1. Then if I now combine both of them, because I don't know, I'm going to find intersection B union intersection C. So let's see. So A intersection B union A intersection C. If I combine both of them together in ascending order, really, like I always like to do, this is like saying 1, 6. So you can see that for 1 and 2, we add the same value, 1, 6, 1, 6. Whichever one you find as an easier approach. So I think the larger your number. So imagine if B was very, very, very large and C was very, very large. You don't want to now join two of them together if they have like different values. That would be so much work. What you can just do, I can find the intersection. That's where this second formula would actually come in very handy, right? So it's just based on use case. There are some that it's okay to do maybe the first guy if it's something very small, just do B union C and find the intersection with A. Or if it's very large, you can do intersection B, then intersection C, then join them together. So I want you to try A union B intersection C and A union B intersection A union C and see if you have the same answer, and then ask yourself which of this particular approach would you like to use. Welcome back. Let's see what we had first. So we had 1, 6, 1, 6, and let's see what you should have had. You should have had 1, 2, 3, 5, 6. 1, 2, 3, 5, 6. If you had 1, 2, 3, 5, 6, well done. If you didn't, you can always go back and try it again. Failure is not fatal. And let's go to the next law. De Morgan's law. What does De Morgan say? De Morgan says that if I have A union B and I'm trying to find the complement of A union B, like saying find the complement of everything. So the complement of A would be A complement, right? Or you can see sometimes you'll say prime here, but I prefer to use this C because it's more descriptive. So it's saying if you have A union B and then you're trying to find the complement of everything, just find the complement of each of everything. So the complement of A is A complement. Complement of union is intersection. The complement of B is B complement. So any way you want to do it is so if it's something very large, right, and you have to first do A union B, that might be so much work. Then I'll find the complement again, that might be so much work. And that way that I can do is I can find the A complement of A, complement of B, and then find the intersection. Also the same thing too. If you have the intersection, you're trying to find the complement of this guy, you can say that everything is inside brackets. Always note that it's inside brackets. It's like saying find the complement of every guy inside the brackets. Complement of A is A complement. Complement of intersection is union. Complement of B is B complement. So let's see some examples to bring this home. Now we have a universal set that contains numbers 1 to 10. We have sets A which contains numbers 1, 2, 3, 6. Sets B which contains 4, 5, 6. And we should find this guy. So I'll solve I and I. You solve I and IV, and then we can compare our answers. So we're trying to find A union B complements A complements intersection B complements A intersection B complements A complements union B complements. So let's see. If I find A union B, my A union B is going to be 1, 2, 3. Okay, so there's 4 and 5 and 6. 4, 5, 6 here. If I find the complement of this should be what is in the universal set that is not in my A union B set, and that's going to be what? Great. 7, 8, 9, 10. Right, so I want to try A complementation, B complement, and see if you have the same answer. Like I said, you're the one that want to decide which you want to use, and I've told you where to use which. Now for the number 3, we have A intersection B, then finding the complement. If I do A intersection B, where does A intersect with B? Right, they only have 6 in common. So if I say A intersection B, that's going to give me 6. And if I find the complement, which is A intersection B complement, right, that will be 1, 2, 3, 4, 5. I will not put 6 because that's 5 complement. 7, 8, 9, 10, right? And I close the bracket. So I want you to try A complement union B complement and see if you're going to have the same answer. Well done. Let's check it together. This is our answer for this guy. See the same thing. This is our answer. You can see number 6 is missing, and you should get the same thing for IV. So that's basically it about the law. Now, for this number 6 law, which is the complement law, we're going to be looking at it together. It's just logic. A complement is what is in the universal set that is not in A, right? So by the time I have A complement, I'll be having the things that are in the universal set that is not in A. Now, if I now do complement again of that particular thing, it just makes sense that I arrive back at A. Let me quickly show this. So if our universal set was, let's say 1, 2, 3, 4, 5, right? And then our set A is, let's say 2 and 3, right? If I do A complement will be what? 1, 4, 5, right? If I now do the complement of this A complement, so if I say A complement, right? That's like saying what is inside the universal set that is not inside A complement, and what is inside the universal set that is not inside A complement. You see that it's going to be 2 and 3, and you can see that at the end of the day we have arrived back at our A. So if you find the complement of A complement, I'm going to arrive at A back. That makes sense. If I find the complement of the universal set, it's going to give me the null set now, because the universal set is everything. Like it's like the almighty set where every other set comes from, right? So if I find the complement of that, that's going to be the null set. Look at something. If we have A union A complement, we're going to have universal sets. So if you look at our listing, if I join A and A complement, because A is this A complement is whatever is in the universal set that is not in A. So by the time I do the complement of both of them, it's going to give me the universal set. You can try these things out. So I mean, the joy is when you try it out yourself and you see it for yourself. I don't want to rob you of that joy. So try it out yourself and see that when you do the union of A and A complements, you see that you have the universal set. Also, so by the time we do A intersection A complements, because A is A, I mean A complement is whatever is in the universal set that is not in A, and by the time you do the intersection of both of them, of course there is not going to be anything. If you look at our diagram here, you can see that there's nothing that joins them together. So if I find the intersection of these two, it's going to give me the null set. Then the complement of the null set is the universal set. These things are just logic, right? Complement of the null set is the universal set. We're going to the identity law. What is identity law? It's saying if I do A union an empty set, of course that's going to give me A. You can try it out yourself. A union nothing is going to give you, like saying A plus 0. A plus 0 is going to give you A. So A union null set is going to give you A. A intersection universal sets is going to give you A. You can try this out yourself. So if you have the universal sets, you have A, and you're trying to find the intersection between both of them, you're going to get your A back. A union the universal sets. A union universal is going to give you universal sets. These are things that you can try out yourself and see, right? If I have the universal set, I'm trying to find the union of it with one of its subsets. Remember, A is a subset of the universal set. If A is also a universal set and I'm trying to do the union, of course, I'm going to get the universal sets back. And then if I do A intersection null sets, so I'm trying to find what A has with null. Of course, A does not have anything with null, and that's why the answer is going to be null. So try it out yourself. Give yourself a test case. The laws of set are actually very interesting when you actually try them out yourself with examples. In the next video, we're going to be looking at Venn diagrams and how to shade Venn diagrams. Trust me, you're going to like it. So if you found this video useful, like this video. And if you found, I mean, if it's just a support to say, hey, well done to what you're doing, or I didn't understand this, drop the comment. I will respond to all comments. And look at our community section of this particular channel, right? Engage with the contents that are there. I post some puzzles, some quizzes, sometimes feedback form, and all these things. See you guys in the next video.